Hello, and welcome to episode 153. And this week we are going to be doing a walkthrough of the Capture the Flag event that we did this week. So, for those that weren't aware, we had eBPF Summit this week, which we have been doing for the last 4 or 5 years. It was a lot of fun. We had over 30 different talks on a variety of different areas around eBPF. And every year we do an eBPF Capture the Flag, which is a fun event that one of the team put together a variety of challenges for people to make their way through to try and solve and get to the end of the Capture the Flag event. I was fortunate to do the Capture the Flag event last year. We did a walkthrough of that. The challenge was a bit different. So last year's Capture the Flag challenge, we used eBPF to hook into a bunch of kernel probes, which stopped you being able to find a process. So if you did PSCF or tried to look in the proc file system, something was happening, a process was running, the eBPF programs would effectively hide the process from you. So the idea really of that challenge was to find a way of locating that process, send it the correct terminal, send it the correct signal, and it would reveal its secrets, and you would capture the flag as such. And every year we have these amazing stories that are usually written by Quentin. So again, big shout out to Quentin for writing these intros and outros all in the Star Wars themed. So yeah, once you solved it, you give them the code and whatnot, and you'd solved it. There was an additional thing that the code that they gave out was also encrypted, and that string effectively was how long it had taken you to solve the challenge and a few other things. It was a lot of fun. A lot of people tackled it in a bunch of different ways. People used things like Tetragon to look under the covers with eBPF, looking at eBPF and things like that. Some people used Inspector Gadget. Some people wrote bits of code to do it and things like that. It was a lot of fun. It was pretty excellent seeing a bunch of different ways that people attack the challenges. But the feedback was really that people wanted a bit more. Some people said that it was too easy. Other people said that it was too hard. So, this year, as Duffy mentioned, like I may have gone a bit too far. I don't know. But so this year I put together a much bigger Capture the Flag challenge. And like 2 hours into the eBPF Summit, starting to get a little bit worried that nobody had actually got to the end of it. But luckily, I think about half an hour or an hour or so before we wrapped up the eBPF Summit, the first person managed to get to the end. And we started to see then more and more people started to solve it as well. So at least from my experience, or from what I can tell, I think a lot of people kind of enjoyed the Capture the Flag event that we did this year. And as mentioned, it wasn't just one challenge. We actually put together a number of challenges, and kind of the story expanded as you made your way through them. So as I mentioned on this particular echo session, we're going to walk through the Capture the Flag. We'll get the source code up and we'll look at various sides of it. If you have any questions, if my screen's too small, this is going to be code and terminal and things like that, then please post a comment, let me know. If you just want to say hi, then do that as well. So let's kind of kick things off. So I've already started the VM. So every year we distribute the Capture the Flag using the Lima VM project. Makes it kind of simple for people to spin up their own copy of it. So I will just quickly pop a terminal up. Bear with me a second. And here we are. So So when you deploy your VM, it will actually tell you what to do. The first step is it requires two terminals, because we have one terminal that's running the capture the flag engine, as it were. So, you know, kind of the entire story here was you're one of the rebel fleet that's attacking the TIE fighter mainframe or whatever. So if we start up, you know, this is basically meant to look like, I would imagine, what it's like when you log into the TIE fighter mainframe. Yeah, so we'll try and log in with my username. It tells me that the user doesn't exist. I'm a part of the Empire, the Evil Empire, etc. So I have 2 hours. We can see here that there are 4 security locks that are all part of the challenge. So each of these locks has a different way of being solved. And on the on the capture the flag repository, there is, as I mentioned, there's a full story that leads into them. And then each one of these security locks requires a different way of solving it. Good question. So for those that come to find Liz today, Liz is on a flight to Austria. No, is it Austria? She's on a flight to Vienna. She's going to be at Open Source Summit all of next week. So that's why it's just myself this week on the eCHO live stream. So we can see here all of the locks are green, so they're all locked. We can see the first challenge really is that one of the maps are corrupt. So if we pop out of here, and I will bring up, there we go, a second, this terminal window, and we can step in and we can start to work out what's actually happening. All right, so my audio just kind of went out then. Let me just double check that that's working. Yeah, cool. So inside the VM, it runs code server. So the entire environment is set for you. There's a Go compiler, there's a C compiler, there's all the eBPF headers in there. But yeah, the first step is to fix this corrupt map. And basically, let me get the actual repository as well. So let me just get the capture the flag repository so we can see those clues. Here we are. Just pop this in here. So this is the repository that has all of the code in here and things like that. It tells you what to do in the second shell. So this is what you need to do in order to start up a code server instance, which is the same as Visual Code. So that is also running inside that VM for you. It automatically will create a eBPF repository, eBPF folder, and inside of there is all of the source code that you will need in order to solve all of the challenges. And then we have the actual challenge itself. So we have this fantastic backstory that all lives within the Star Wars universe and follows on from all of the previous challenges. And then, yeah, we have clues for each of the security locks. So the first clue is that we can use BPF tool. Second clue is, and I'll do it in the terminal in here. I'll need to make this a little bigger, so bear with me. Right, so actually that's not going to work. So we can see here there are thousands of maps that are all attributed to the Empire. So we know that one of the maps, well, we know the map that is the broken map. So if we sorry, let's find the map's ID. So the map is 6. Right, so we can see here as part of the clues, our hacker may have got it the wrong way around. He was hacking this map. So effectively the clue here is that the contents of this map are the wrong way around. So effectively what we need to do is we need to take all of this data and send it the other way around. To make life a little bit easier, I put something together to make it a bit quick for us to do that. So if I quickly set that. Oops. Right, so effectively what this is going to do is it will rearrange the contents of that map so that the values have been completely turned around. As part of the challenge, you'd have to do that manually, and you'd have to do effectively this, which is a BPF tool, update ID, the ID of the map itself, which is 6, and then we're updating the value of the first key with all of this, but the other way around. So start from 72, 47, 52, 4A, etc. And if we quickly stop sharing this screen for a second, but if we pop back to our other screen, let me bring my terminal back up again. And in you come. We can now see that the map has been disengaged. We are now, that map that was corrupt has been fixed, but now it's saying a map that it's expecting is missing. So we've completed the first lock, we've completed the first challenge. We're now on to the second lock. The idea behind this first challenge really was to get people using BPF tool a bit more. So it was kind of interesting. My thought process really was we could either just focus on doing pure coding challenges, or do we want people to learn how to use kind of the command line tooling all around eBPF and eBPF maps and things like that as well. So I thought it makes sense to kind of have a mix of the two. So that's the first challenge down. We go back to my coding window, as it were, back over here. Right, so so there are two ways to tackle this problem. As you can see, it was saying that the map was actually missing, so we need to create a new map. What I did, I brought my terminal window back again. Here we go. What I did add is some example code for people. Let me just shrink this down a bit. So we have here some Go code that's using the Cilium eBPF library. Most of it's kind of here, skeleton, as it were, for actually creating a map. And this largely is the bit that we kind of care about, wanting to create a new map. So the name of the map that was missing was Empire BOF. One additional clue was in here, was that the spy knew that the data that existed was this data here. So this is the data that we're going to populate our map with in the first key. And if I shall just so it's just going to quickly get the dependencies for me in my terminal window. I'm not sure if it's going to make my terminal any bigger, unfortunately. That doesn't look like it. So my program has run. I have exited. In the other window, which I'll show you in a second, the map unlocked, and then it locked itself back up again. Now, the reason for this is that eBPF maps only exist as long as they have so these are reference count, basically. So I can create a map whilst my program is running. When my program ends, my reference to that map is removed. So it went from having 1 holder to 0 holders, at which point then it's kind of garbage collected and tidied up. So if I kind of cheat a little bit here and leave my program running in the background for an hour, hang on. Let's add in that missing library because we're using the time library. So now, there we go. So now what we have is we have a program that's actually running, it's created a map, and it's holding a reference to that map. Now, that is with code, and your program running, they're interacting with maps, they're going to be holding references to those maps. If you were to use BPF tool for this, to create the map, what you would be creating is a pinned map in order for it to persist. And the way that that actually works is your map is pinned to a file on the BPF file system. So there's a reason why we have pinned maps. That main reason really is if you want to have multiple programs, eBPF programs or userland programs that are all wanting to interact with the same map, then when it is pinned, other programs, etc., can actually make use of that pinned map, and you can share it between different running programs. So I will quickly pop back to my other screen. We can now see, once I bring this window in, that the second lock has now been deactivated, and now the authentication waiting for some sort of authorization on port 2000. So we've done the first two. We've done the first two challenges. They're largely focused around maps. The first one largely making use of BPF tool. The second one we largely made use of a bit of Go, or you could use BPF tool, but a bit of Go and the Cilium eBPF library in order to create that map and hold a reference to it. So I also kind of ramped these challenges up. So to make them a little bit harder, there's going to be more and more kind of code that's actually required. And other things will start to make life a little bit harder for you. So let's start to look at the code that we need for challenge number 3. Go back to my window. Right. So if we look at the repository, part 3, getting authenticated. There's a couple of clues here, but effectively the long story short is that a thing is meant to be sending traffic to port 2000 in our mainframe machine. And there is some example code that one of the engineers tried to put together, which is an eBPF redirect folder. I should kind of apologize to Liz when she first ran through this as a test. I put the directories the wrong way around. So Liz spent about 2 hours wondering why the code was doing really random things and nothing really related to what the actual problem was. But if we look at the clues, something is generating traffic on the loopback interface. The numbers don't seem to add up, and I'll explain kind of what this means in a second. And then traffic needs redirecting to the right place. So if we go to the redirect folder in here. So we don't really need to worry too much. Let me move this down and make it a little bit smaller. We don't need to worry too much about the Go code. All of that is kind of really largely all taken care of for you. It's going to use the loopback interface. This is largely all going to be within the eBPF code itself. So most of this is pretty much boilerplate for anybody who's written any code that kind of has to do any sort of networking. So kind of quickly step through some of this. We are actually, I'll go to the bottom first. So 2 hooks, one we attach to ingress, one we attach to egress. So looking at both sides of the traffic. When traffic comes through TC on either ingress or egress, we will inspect that traffic, ensure it's the right sort of traffic. Is the protocol IP? So is it protocol we care about? And then is it TCP traffic that we're expecting, etc.? If so, then get those headers. And then this is where we need to start kind of looking at what's actually happening. So here we are getting the source and destination of the traffic as it comes in. And this here will say whether it's ingress or egress as it's kind of coming in and out. So if I kind of pop into this directory and run it, so I'll make this a bit bigger for a second. I'm going to run a go generate, because go generate, for anybody who's not done this before, will turn all of our eBPF C code. It will compile it into an object, and then it will add it to our Go code so that our Go program can load it at runtime. So now if I do a Go run exec sudo, because you need sudo privileges. So it's just going to quickly compile. Oop, what have I done wrong here? Oh. There we go. So we can see down at the bottom, there's lots of traffic that's going back and forth, but that doesn't look right. We know what ports things should be going on. There, well, can we see some Imperium traffic in here somewhere? But effectively, we're not seeing the right traffic. So why is that? So shrink this down a little bit. So as mentioned in the notes here, one of the engineers was muttering something about endianness. Now, this can be quite confusing if you're kind of not aware of it to begin with. But when we're dealing with numbers from a networking perspective, then they tend to be a networking byte order as opposed to host byte order. So that effectively means that the numbers are kind of read backwards, which means the number 1024, well, the number 2000 and 2001 that we care about are actually completely different. So what we're actually going to do is there we go. I think that's right. There are helper functions that exist. So this is a helper function BPF HTONS. That stands for host to network space. That will convert the network type of number to a number that makes a little bit more sense to us. So if I do a go generate again, so it recompiles our C source code. There we go. So now we can actually see, let me make this a little bit bigger. We can now actually see the traffic that's coming in to the right port. So what's meant to be happening is the Imperium system is listening on 2000, but the traffic is being sent to 2001. So what we're actually going to do now is we're going to redirect that traffic to the right port. So if I shrink this down a little bit here. So what we're going to do now is if it's coming into, so if it's ingress traffic, so it's something trying to connect to our port, if the destination is 2001, then change it to 2000 as the destination. So we're basically we're doing a port redirect. However, we need to change this number to network space because it's going to be used by the network code. So another helper, network to host space. So now, when traffic is sent to 2001, we will see it. We will change that port from 2001 to 2000, and traffic then will go back onto the network. So here is where we rewrite the header, and then later down here we basically drop it back onto the network. However, this isn't going to work because if you think about what's actually happening, is one program is sending traffic that it knows about to 2001. Something is receiving it on 2000 and then sending it back to 2000, where nothing's listening where nothing is expecting it. So we're actually confusing what's actually happening here. So on the egress side of things, we need to kind of do the opposite of this. So if we grab this, so in egress, if the destination is 2000, we need to set the source to 2001. So now, if I've done this correct, oops, I need to go generate to recompile the code. Oop, is that right? I've done this the other way around. Bear with me. Right. So what we've done here is we've done the port changes on both sides. So if we're trying to go to 2001, change it to 2000. If traffic is coming back from 2000, change it back to 2001, so that effectively both sides of user land are seeing things in the right way. We're kind of doing the man in the middle in terms of changing those ports around, and then traffic is all going as expected. So now we have actually solved problem number 3. So I'll quickly show you my screen. Pop back to my terminal. We can now see it waited for traffic on 2000, even though the program was trying to send it on 2001. We kind of man in the middle that traffic with eBPF. We changed it from being sent to 2001 to 2000 and ensured the traffic in both directions worked end to end. So it got the packets that it was actually expecting, now actually authorized. And the final challenge is for our code to be trying to speak to an external system for an external mainframe, as it were. So this is the 4th challenge. Let me bring my window up one final time. All right. So part 4, access the mainframe. So according to this clue, one of the rebel engineers has effectively managed to create a fake mainframe that will satisfy the requirements of the TIE fighter system. He's written most of that code. It's all in this response directory. Unfortunately, after fighting with the verifier so long, he smashed his keyboard up and refused to work on it any further. So this problem is largely where you're going to kind of butt up against the eBPF verifier. For people who've not had to write an eBPF code or anything like that. The verifier is largely going to be the thing that you kind of come up against more than not. And the verifier there is really to ensure that the code that you are running is stable, safe, and secure, and isn't going to jeopardize the health of the running system, things like that. So the verifier generally tends to be the system that's in your way from you breaking your own computer, as it were, which is a good thing, but it means there's extra thought a lot of the time that you need to think about when you are writing code. So the first clue is we'll need to fix the code so that it passes the eBPF verifier. And the second clue is we'll need to change some of the data. So let's pop into the code for this one. And this is in this response folder. So again, we don't need to worry about any of the Go code. This is all boilerplate for loading our eBPF program and attaching it to an interface. So if you look at the eBPF code itself, let me shrink this a little bit. A lot of it is the same. So down here at the bottom are our two hooks that attach our program both in ingress and egress. Pardon me. The bits that we need to kind of really care about, as mentioned, same thing again. So is it IP? That's good. We want IP. This time it's UDP that we're caring about. So we can see UDP data flying around. Get that UDP header. We're looking at source and destination. And then what we're doing here is getting the data that's actually inside the packet. So if you get a whole packet, you'll have an Ethernet header on it. It will more than likely have an IP header after the Ethernet header. And then it will have either a TCP header or UDP header. After that is the actual data that we care about. So what we're doing is we're getting the offset. So we're working out how big those headers are. And then we've got a pointer to what's after all those. And we know how big the packet is. So if another packet is like 100, we know all of those headers add up to 96 bytes. The remaining 4 bytes are effectively the payload that's actually in there. So we're getting that payload. We are reading that payload into a data buffer here. And then we're going to print that out so that we can see it. So if we try and run our program, let me go into the redirect folder and to the response folder. If we do a go generate, I'll take a second. It's just going to grab any dependencies and compile our Go code. Now, if we try and run our code, it's going to compile it and it's going to try and run our program. I'll make this a little bit bigger so you can see what's kind of going on. So one of the things I did in the hope that this might make people's lives a bit easier was really crank up the verifier verbosity. I made that a little bit bigger, but effectively, this is a massive stack trace from eBPF, the eBPF verifier. And we see here like the actual lines that the code lines that are being executed, kind of look like and whatnot. But if we look down at the bottom here, we can see here that there's an invalid memory access from this line here, which is what we're trying to do with this line here is copy the source MAC address into a buffer. And for whatever reason, trying to access that variable internally is causing the verifier to give us this huge error. So there's something wrong with those bits of data that we're going to access. So if we look at this code here, if we pop back, the line that it's complaining about, it's a little bit smaller. So yeah, is here. So as I mentioned, we have a data buffer of however long that is. Was that reference? That is 6. So that's how big a MAC address is. So we've created a buffer that's 6 bytes long. We've got this buffer that's created for us. We have the original MAC address here, and the amount of data we want to copy is 6. So we're trying to get that source MAC address and copy it into our buffer. However, for whatever reason, trying to access this is causing us a problem. There's something actually wrong with it. So what is actually causing a problem with that? So if I'll just quickly comment this out, and we'll go into detail about what's actually happening in a second. If I quickly go generate again and start our program, we can now see that it's actually running okay. So effectively something, and we can see here now that we're actually printing out what's actually kind of happening. So we can see that there is data going about, and we can see that that data is 3 bytes, and it's SYN, like you would expect with TCP, SYN, and ACK, etc. But yeah, so shrink this a little bit. Effectively, something to do with this function is breaking everything afterwards. Now, let's see if I can get the kernel docs open for this function to explain what's actually happening. Right, so I'll make this a bit bigger as well. So this is the clue, basically. So if we use the BPF store bytes function, and this is a great function for being able to modify an existing packet as such, a bunch of reasons, but mainly because it will recompute all of the checksums. So if you change data, any of the checksums that were created originally will be invalid. However, as it says in the text here, that changing of the data and checksums and things like that will invalidate any pointers previously that were validated. So what's actually happened here is this Ethernet struct that we have and the data that it's pointing to, if we go back to find its definition, which is here, there we go. So this is pointing to data, and data is pointing to the underlying FTP socket buffer. Effectively, they've been verified here. The verifier is happy that that data points to that, and the values exist if they're checked, etc. When we run this function underneath here, the store byte, all of those pointers are invalidated by the verifier. So it can no longer guarantee that we're pointing to the right bit of data. It can't be sure that we're still pointing to the Ethernet header, and we're still pointing to like that variable inside the struct and things like that. So that is why the verifier is getting angry with us, because now all of that validation is completely out the window, and it can't be sure what's actually happening inside the program itself. So what we can do, and this is a quick and easy fix effectively, is to put this code in a different place. So all of this is fine. We're copying everything all out so that we can swap things around. We're changing these, but we're not actually accessing any of the... It's only these issues where we're accessing things that are being pointed to, basically. So if we put it down here, and I'll uncomment this now. If I recompile this, so now our code is fine, and we are able to store those bytes because we're not accessing any of the pointers afterwards. And one thing that we're doing as well is we are getting data, and we're changing, because it's a 3-byte array. We can actually then change that data, and then this store bytes will write that at the right place, which is at this offset. And then this flag here is to recompute all of those checksums. So we're changing the first byte to a question mark. So I'll just quickly show you what's actually happening in the capture flag. Stop sharing the screen. Share the screen here and pop back to my window, bring it in. So now we can see it's gone from being a sin, because the first byte has now been changed to a question mark. So what we've actually done in eBPF is emulate a response of another system. There's nothing on the other end. eBPF is seeing this UDP packet, reading its data. We are changing the source and destination around in much the way that we did in the previous challenge, but now we're actually also going to change the contents of the packet itself. So if I just do one last change, I'll stop sharing this. I'll share this window one last time and bring it in. So we know that it's a sin, and if you've done anything with TCP, the response to a sin is an ACK. So the clue here is that we need to acknowledge the mainframe, the Imperium system. So we'll need to change a couple more of these bytes. So we'll need to change bytes 0, 1, and 2. And as mentioned, the opposite of sin is an ACK. So now, go generate, recompile our C code, and we are going to run our program. And now, there we go. Let me go back to my screen quickly. And bring it in. Boom. There, we can see it got that acknowledgement. The final security lock was undone. You have your key to paste into the eBPF Summit channel. The system is shut down, and you get your outro story. So that has been a walkthrough of all of the 4 challenges that we put together for this year's Capture the Flag. I hope you all enjoyed participating in both eBPF Summit and the Capture the Flag event itself. I had a lot of people sending me DMs asking for help and things like that, which was kind of amusing. We're trying to, as I'm always happy to help people out, but yeah, it was good to see some people get to the end of it before the end of the eBPF Summit. Yeah, and I hope that was a good challenge for you. The Capture the Flag last year's and this year's and previous years are all within the Iceberg repo. So if you want to run through everything that you've seen today, fire up Lima, fire up the Capture the Flag YAML, it'll get that VM for you. You can step through all of those challenges, learn a bit of eBPF if that's something that you're wanting to get your head around. Have a fight with a verifier, as most people do. And yeah, hopefully make your way through it and kind of get a little bit more knowledge of eBPF. So with that, I think that's pretty much everything that I was hoping to cover in this year's Capture the Flag event. With a bit of a wrap up, we've got a number of events that we're going to be at over the next couple of weeks and months. So if you are based in the UK or traveling to the UK, there is going to be Kubernetes Community Day in October. I will be doing a session all around running and writing eBPF programs to run within Kubernetes. There's a lot of challenges that kind of come with running inside of Kubernetes, knowing which interface you're actually sending traffic through and tapping to. hooking into programs and kind of where libraries are and things like that. So I'll be kind of doing a talk all around all of that. And then KubeCon in Salt Lake City in Utah in November. A lot of the team who are part of the Cilium project working on eBPF will be there. There will be the community booth. If you have eBPF questions and you're going to be at that conference, go find people, ask them questions, and get to know people and things like that. So I'd like to say thank you very much, everybody who joined today's session on both eBPF and the Capture the Flag event. Enjoy the rest of your day, and I will see you all later. Thank you.